Hello everyone, this is Yeli. In this video, I'm going to talk about one of my papers, Quasi revenue neutral congestion pricing in cities, crediting drivers to avoid city centers. Congestion pricing is a well-known traffic management strategy that mainly applies at major highways or urban areas to curb excess demand for entering congested areas during heavy traffic period. There are several cities have been implemented congestion pricing schemes such as Singapore, London, etc. Well, we know that greatly increasing number of vehicles has led to severe congestion in urban cities, especially during morning peak hours. So several network-level traffic management methods have been developed for complex urban cities, such as perimeter control and congestion pricing. Previously, we have developed two kinds of perimeter control approaches with fixed cordon and dynamic cordon respectively. And you can refer to the previous videos if you're interested in. So in this paper, we will consider congestion pricing strategy based on macroscopic fundamental diagram to investigate its effectiveness to improve the network performance. We noticed that previous MFD-based pricing literature mostly consider one or two regions in the network, while multi-region network should be taken into account. So in this research, we consider a heterogeneous network with 7 homogeneous regions, as shown in the figure. Region 7 is assumed to be the city center. The proposed congestion pricing method will provide different tolls for each region, and the tolls change over time based on the congestion level in related region. In our research, we consider the tolls collected from the users based on the route they have traveled between region-to-region node pairs. During morning commute, from region 1 to region 4, for example, the figure shows 3 possible routes, but actually there are several routes between any 2 regions. So one of the 3 possible routes might be more congested since it passes region 7, the CBD area. Well, we know that the CBD area might be more congested in morning commute hours, and the vehicles are charged based on the congestion level of each region. That is, if the travelers travel through uncongested regions, then they may not need to pay, or maybe they can receive some money back. Otherwise, the travelers should pay the tolls. The pricing is dynamic since the tolls of each region fluctuate according to current congestion level of each region. And we embedded a current best case shortest path route choice model according to total toll needs to pay from one region to another. So here, the toll paid of one road is the sum of tolls of all past regions, but not including origin and destination regions. For example, on the road 1654, the toll paid is the sum of tolls in region 6 and region 5. This is done on purpose since travelers cannot easily shift their home or working locations. So tolling those people would lead to more opposition of the pricing scheme implementation. Okay, now let's move to the research framework. As shown in the figure, we employed model predictive control to update the tolls of each region. And then we use a detailed MFD model to represent the real network in our simulation. The controller adjusts the toll of each region at a predefined time interval. For example, maybe every 5 minutes, the tolls might be updated based on the current accumulation of each region. Using model predictive control is to achieve multi-goals at the same time. One is minimizing vehicles' total time spent in the network, and the other one is keeping total toll paid of the whole network close to 0. That is maintaining revenue neutral. Well, the concept of revenue neutral is that all revenues obtained from a pricing system are returned to the traveler through some mechanisms. For example, the pricing scheme imposes positive tolls on congested regions and negative tolls for uncongested regions. But it should be mentioned that the negative tolls does not mean directly give money back to the users. It perhaps through giving credits for public transport or maybe provide discount for vehicle registration fee. So the total toll paid of the network is close to zero. In this paper, we just started with revenue neutral, considering positive tolls collected from travelers who pass congested regions, and negative tolls for people who use uncongested regions. So future works might consider how to distribute the revenue to travelers. There are two MFD models developed in this paper, optimization and simulation models. The optimization model is the input model for MPC, and the simulation model is the real network, that is the plant. It should be mentioned that the LSTM neural network is adopted in the optimization model to estimate the traffic flows between regions without knowing the destination information. Well, let's see the results. We compare 6 control scenarios to show the performance of the proposed congestion pricing scheme. A proportional integral controller is adopted for comparison purpose. The figures show the accumulation evolution of each case. So in general, the toll cases makes the vehicle more uniformly distributed in the whole network, and the network is cleared earlier than the no toll case. Besides, the accumulation heterogeneity of the network is further mitigated with negative tolls, as shown in Figure C and Figure F, compared to Figure B and Figure E, respectively. It should be mentioned that MPC outperforms the PI control cases since the CBD area, Region 7, is less congested. The applied toll in each region are indicated in the figures. At the very beginning of the simulation time, like from 0 to 600 seconds, there is no toll since all regions are uncongested. Then Region 7 become congested, and the controllers pursue to protect Region 7 by implementing higher tolls. Comparing to PI controller, the tolls in MPC scenarios are not fluctuate between the whole toll ranges, while the toll values in PI controller are very active over the studied period. The table shows the statistics for 6 cases. We can see that the MPC with negative tolls performs the best with respect to total time spent, about 12% reduction, and the average toll collected from a vehicle is about $0.09. So based on the above results, we can conclude that the proposed pricing strategy is able to improve the network performance and maintain revenue neutral. Alright, thanks for watching this video.